Good morning, all of you. In today's session, we are going to start with the 10th standard chemistry and physics. Unit 10 electromagnetism. Series 5 is going to be discussed. In the earlier session, we completed what is meant by electrical current and magnetism, how both are correlated with each other, and what are the devices which used to measure the direction and the strength of the current. So those topics were completed, and we are learning all these based on activity. Scientific activities are going to be performed based on that activity. So learning of these concepts are possible. In addition to all this, Unit 1 to Unit 9, entire detailed explanation available on the channel called the World of Competitive Chemistry. In this series 5, we are going to discuss about magnetic flux and magnetic flux density. These topics are going to be introduced. Let us enter into our today's concept, series 5 of Unit 10, electromagnetism. Yes. Magnetic flux and magnetic flux density. So in order to explain this, here the diagram was given to us. Consider a uniform magnetic in a space. So we are taking a magnetic field, so that are unidirectional in nature. Instead of curvature, we are assuming that all the magnetic field lines are passing in the regular manner. All these are parallel in nature. Imagine a plane of certain area A was placed perpendicular to the field at a certain point. So here you can clearly observe this is a hypothetical circle which we kept up through which these lines are passing. And this is said to be a area A. Now, in the magnetic field I have shown in the figure, you notice that a few field lines are passing through this one. It is not possible to accumulate all the lines through this one. Pass all the lines through this one. Rather, few of the lines in these magnetic field lines are passing through this one, and the remaining are unaffected. So these number of lines give the estimation of strength of the field which is moving through the this area A. So extent of lines, number of lines which are moving through this one will give the strength of the magnetic field. How extent the density will be there, that extent the strength is assigned to that given magnet. Let us see in detail. The number of lines passing through the plane of the area A perpendicular to the field called magnetic flux. Here, how many lines, how many number of lines which are passing through this area A in the given time are denoted as a magnetic flux. So that are perpendicular to the A. So A was kept like this. A was in the 90 degrees angle. When 90 degrees angle will be there, then only we can say perpendicular in nature, right? So which are perpendicular both to each other. Now, so here number of lines which are moving through this area A in certain time, that is denoted as a magnetic flux. And here we have the symbol called pi. Here north pole and south pole is assigned for the given magnet, and imaginary sphere are imaginary thing was kept in between, so that how many lines are moving, because always from the north to south, always there is a movement of field lines. So always there is a movement of field lines. So earlier we assumed that all are moving in the curvature. Now we converting those curvature lines into a parallel lines. These parallel lines, straight lines are moving from north to south. When these are moving here, imaginary hypothetical sphere was kept in between, so that within the given time, how many lines are moving through this one is denoted as a magnetic flux, and the symbol which denotes this one will be a pi. Magnetic flux represents the number of lines passing through the imaginary plane in the given field. Of course, flux depends upon the orientation of the plane in the field. So in what orientation it was inclined, based on its orientation, how many lines are passing through this one will depends. Because if it is in the slanting position, passing of line will be more. If it is in a perpendicular position, that extent of line movement will be somewhat less. In that manner, so based on the inclination of the area A in between north and the south poles of the given magnet, then only we can decide the strength of that given magnetic field. But here we are concerned only with the perpendicular case. Always the case the inclination was kept a constant, and we are assuming always it should be in the perpendicular position. So when perpendicular orientation of this area A was there in between north and south poles, and when lines are moving through this one in the unit time, how many lines are moving through this kind of area is denoted as its magnetic flux. And we have SI units for, in order to represent this magnetic flux, SI units for the magnetic flux are Weber. So Weber are the unit for this one. Now, strength of the field is easily defined using idea of flux. If flux, a magnetic flux term is known to us, then it is very simple to denote the strength of the magnetic field. If the imagined plane is perpendicular to the field and has a unit area, flux through this plane of unit area gives the strength of the field. See, what's the relation between the flux and strength of the magnetic field? Just let us correlate both the things. The flux through which the plane unit area gives the strength of the field within this area. So what we are considering, the area which is covered by this point A, the sphere A. So when these lines are moving through this one, now it is assigned as the strength of the field as well, right? So imaginary plane perpendicularly it was kept, and this unit area was taken into the consideration. And how many hypothetical lines, number of hypothetical lines which are moving through this this sphere is said to be a strength of the field as well. The strength of the field technically called as a magnetic flux density. There is a slight difference between the magnetic flux and magnetic flux density. And flux density is a term which is denoted with the parameter called a B. So magnetic flux density is defined as a magnetic flux which is moving through the unit area. So this was taken as a unit area. How many lines are moving through this one is denoted as a magnetic flux density. And that will be perpendicular to the field. Whenever we are taking a straight lines and exactly opposite direction sphere was placed in between, that is called a perpendicular. Perpendicular in the sense both are in the opposite inclination. So here the new kind of thing was introduced, that is called the magnetic flux density. That magnetic flux density is denoted with the B, and it is called magnetic field induction as well. Magnetic flux density alternatively known as a magnetic field induction. Magnetic flux density is always denoted with a parameter called a B. Now, let us find a few important differences between, slight distinction between magnetic flux and flux density. Always, magnetic flux can be denoted as a pi, and a pi with a B as well. Otherwise, in the magnetic flux density always given with the parameter B. Magnetic flux is expressed in Weber units. WB are the units for that one. But in case of magnetic flux density, this will be given by Weber meter inverse 2. What are the units? Weber meter inverse 2. So which in turn called as a Tesla. So Tesla denoted with a capital T. And the always magnetic flux will be the scalar quantity. Scalar quantity is nothing but measurable quantity. We can scale that. We can identify the quantity. So measurable quantities are called scalar quantities, and the vector quantity in the sense that is the empirical one. So that is magnetic flux density is the vector quantity. Now let us see flux through the area A, and pi will denotes what? Pi will denotes magnetic flux. What is the flux through the unit area perpendicular to the field? Just now we said the flux through the unit area perpendicular to the field is called magnetic flux density. That is denoted with the B, and the units are Weber meter inverse 2, in turn called as a Tesla, and it will be a vector quantity. The ratio of the magnetic flux is nothing but pi, and moving through the plane perpendicular to the area is denoted with A. So here it will be the ratio, that is Q by A. Pi by A. Pi is called a magnetic flux. Pi by A, this ratio is taken as a magnetic flux density. Within that unit area, how many number of lines are moving in a given time is called as a ratio, that is Q by A. sorry, pi by A. That pi by A denotes a magnetic flux density. And magnetic flux density will be denoted with the symbol called B. And always the units and the property of this one will be mentioned here. So there will be a slight distinction between these two terms, magnetic flux and magnetic flux density. And magnetic flux density mathematically represented as a magnetic flux, which can be taken with the ratio of area. So area is denoted with A, magnetic flux is denoted with pi. So now B is equal to pi by A. So if you want to identify magnetic flux from this equation, pi is equal to B. B denotes what? Flux density. And that when multiplied with area, it will become pi is equal to B. SI units of this magnetic flux density are taken as Weber per meter square. Otherwise, Weber meter inverse 2. We can say this as a Weber per meter square. Otherwise, Weber meter inverse 2. So, which in turn called as a Tesla as well, right? So, these are the units and the mathematical representation of magnetic flux density. There is a slight variation between magnetic flux and flux density. Now, we can generalize the formula of flux for any orientation of the plane taken in the field. So earlier we only considered about perpendicular inclination of the plane. So perpendicular inclination of the sphere was taken and how many lines which are moving through that were taken into the consideration. Now we can generalize this one, we can optimize, we can customize this one by changing the inclination. Instead of perpendicular, just we are slanting the position with a certain angle theta. Let theta will be the angle between the magnetic field and the normal to the plane of the area, as shown in the figure 3b. The effective area of the plane perpendicular to the field is A cos theta. Now let us see. This is a sphere. Initially, we are inclining in the perpendicular manner. Now slanting this with the theta. Theta is the angle where magnetic field and a normal plane were making a angle here. That is clearly mentioned in this. That is clearly mentioned in this diagram 3b, where area A now slanting position, and that is making the angle that is called A cos theta. The extent of angle which is originated by the slanting position is A cos theta. Now, this is a formula used when the plane was taken in the angle with the field. So when angular inclination is present, this was taken into the consideration. Otherwise, the normal formula will be B is equal to pi by A, in turn written as a pi is equal to B as well, right? Now, when it is in the slanting position, and we need some extent of correction for this one. Now, it can be represented as B is equal to pi by A cos theta. A is now replaced with A cos theta. B is equal to pi by A cos theta was taken. Theta cos theta is the angle in which angle this sphere was inclined. The flux through the plane is given by. So if we are using B is equal to pi by A cos theta, this is for the magnetic flux density. From this equation also we can derive magnetic flux in the inclination condition, then pi is equal to BA cos theta. So BA cos theta was also taken into the consideration. Now magnetic flux in this inclination is given by pi is equal to BA cos theta. Let us define individual parameters which are mentioned in this chemical equation. Pi is equal to magnetic flux. Pi is the parameter magnetic flux. So that is measured in Webers. And B is the magnetic field strength. B is denoted as a magnetic field strength that is measured in Weber meter inverse 2. Otherwise Tesla. So here Weber is mentioned and magnetic field strength is measured in Tesla. And A is called a cross-sectional area. So that is the hypothetical sphere through which lines are moving. That is the cross-sectional area which is measured in meter square, right? 1 Weber is equal to 1 Tesla meter square. 1 Weber is equal to 1 Tesla meter square was taken into the consideration. So this is for slanting position. Now we entered into the question. Get ready to answer these questions. What is the flux through the plane taken parallel to the field? So here, what is the flux through the plane taken parallel to the field? So where the lines are inclined in the same parallel movement here, in the same parallel movement, we are considering the flux. So in that parallel motion, how the flux is determined? That is the question here. When B is the field, so B is the field. B is nothing but what? Magnetic flux density. So if that is inclined in the parallel motion, which is in the what parallel with respect to the lines which are moving, then the flux through the plane becomes 0. If cross section is in the parallel and even lines moving in the parallel, so all are in the parallel motion only, then what happens? So here we can't assume, we can't identify how many lines are passing through that parallel line. That's the reason why in that case flux through that plane will become 0. When it is in the perpendicular condition, then only flux value will be integer. When it is in slanting position, again we have a correction for that one. In that case also we will get some extent of value. But when it is taken in the parallel one, it will become 0. What becomes 0? Flux will become 0. This is the information collected from the platform called a Brainly. Thank you very much for your valuable information. Now, what is the use of introducing idea of magnetic flux and magnetic flux density? So magnetic flux and magnetic flux density, what is the main purpose of this one? And I collected this answer from Doubtnet. Thank you very much for your valuable information. Magnetic flux density is nothing but it is equals to flux divided by the area. It will be the ratio, and it is represented by the alphabet B, and the units are Tesla. Mathematically, B is the magnetic flux density that is given by flux by area, right? Magnetic flux is nothing but the number of magnetic field lines which are moving through the closed surface, otherwise the area of cross section. Magnetic flux is equal to product of the magnetic field and area. Magnetic field and area were taken into the consideration. Magnetic field is denoted with B, and when it is multiplied with a area of cross section, B into A is equal to pi, because magnetic flux is nothing but pi, right? Pi is equal to B into A. Here the units are Weber. So this is the general difference between these two, and what kind of applications we will find for these two parameters we will discuss in the next session. And one more question is posed here. Are there any sources of magnetic field other than magnets? So magnetic fields, only magnets are used to originate the magnetic field, or any other system is also giving that magnetic field? Let us see. Current carrying straight wires and coils acts as the sources of magnetic fields. So here current carrying straight wires. So current carrying straight wires are nothing but metals only. And another coils. Coils are used to heat. They are used to generate the heating, and electrical coils will be there. So in that condition also magnetic field will be induced, right? Other than magnets, other than pure magnets, so here electricity related devices also inducing, also originating this magnetic flux. Magnetic field will be generated by current carrying wires and also coils, which are also the sources of magnetic field. This is the answer I collected from the platform called Doubtnet. Thank you very much for your valuable answer. Current carrying wires are provided here. You may go with the copper wire, you may go with the silver wire, any kind of aluminum. So all these are current carrying. While passing current, they are able to generate a field around that one. Magnetic field will be generated around that one. So in that case also field will be originated. Now, another application based question was posed here. Do you know how old electrical calling bell work? So how the electrical calling bell is working, then how can we get this? How can we say this is the application of magnetic flux and magnetic field and electromagnetism? I collected this answer from the platform called Doubtnet. Thank you very much for your valuable information. An electrical bell contains the electromagnet. Within the electrical bell, it is composed. The main component of this one will be electromagnet. Electromagnet will work with the vectors of electrical and magnetic as well, consisting coils of insulated wire. Here you can find insulated wires are stripped around these coils, and the rods become magnets. The rods whichever we are taking, these will become like a magnets and attract the piece of iron attached to the clapper. Uh, the clapper his bell and make it ring. So whenever it is going to touch with this iron, what happens? Bell ringing is possible. So here the entire criteria of this calling bell, working of calling bell will be, so here we are taking a magnet, electromagnet was taken here, and two coils were inserted in the parallel manner. These two coils were stripped with the electrical current. Electrical insulated wires were stripped around these two. Right now, in the closer proximity, iron strip was introduced. Here is the iron strip was there, and this iron strip is far away from this bell. So this is the gong, we can say, and here this iron rod at its terminal center have a hammer. Hammer, when hits on the surface of the steel gong, what happens? We will get the noise that will ring like an alarm. So how it will work, let us see. In order to operate the entire thing, we have to get the electrical source from the battery. Battery will supply the current to this one. Otherwise, you may connect with the grid connection also. Here, when we are switching on the bulb, switching on this calling bell, switching on the electrical calling bell, what happens? So here at that instance, what happens? This iron is moving near to this one, moving near to this coiled strips. So when coiled strips are closer with this iron, what happens? It is participated in the vibration. During the vibration, this hammer will strike on the surface of gong, steel gong, several times, so that the alarming sound will originate, and that will give the sense of calling. That will give the sense of calling. So in this manner, electrical calling bell is working. So in this magnetic field which inclined, which originated around these electrical strips, because current is passed, that moving current, because these strips, coils are stripped with these conducting wires, insulated wires, which are originating the magnetic field around that one. Obviously, magnetic field will attract the metals. So magnets. So here, because of this one, whenever we are switching on the calling bell, this iron will be moving towards these insulated wires, insulated coiled wires, so that here hammer will hit on the surface of the steel coated gong, so that here alarming sound will be originated, so that we will get the sense of calling. This is the entire process of calling bell. By this, we completed the session. In this, we discussed in detail about what is magnetic flux density, how both are interrelated, and what are their representing units, and what are the applications of this electromagnetism in our daily life by taking electrical calling bell as an example. Hope this session will helpful for your preparation. Thank you very much for your consistent listening. Thank you, one and all.